Hi, I'm Shan Nawaz. In last lecture we have defined separate exact sequences. But before we proceed further, let us recall what do we mean by separate exact sequences. Suppose we are given our modules, say m, m prime and m double prime, and suppose we have an exact sequence like this where 0 goes into m prime to m double prime m. We have a homomorphism f, and from f to m double prime we have a homomorphism g, and m double prime goes to 0. Then this exact sequence is said to be a separate exact sequence if there exists a map, say h from m double prime to m. So this h is a map from m double prime to m such that this composite map G composite with H. Now obviously if we look at this map, so H is a map from m double prime to m, and G is a map from m to m double prime. So this is the composite map G composite with H. So this G composite H is a map from m double prime to m double prime. Now if this composite map is the identity map on m double prime, then we say this sequence is a separate exact sequence, and this G is said to be a splitting. Now let us prove the following result on separate exact sequences. So we have this proposition. So it states that suppose we are given a separate exact sequence. So if 0 goes to m prime goes to m, and m goes to m double prime, this is the map F, this is the map G. So suppose this is a separate exact sequence. With splitting say H from m double prime to m, then this module m is actually direct sum of f of m prime and h of m double prime, and then we have to prove this direct sum is isomorphic to m prime and m double prime. Let us prove this. Now first of all, so we are given a splitting. So since h from m double prime to m is a splitting, now if this is splitting, then this composite map is the identity map on m double prime. Then we have this composite map G composite with H is actually identity map on m double prime. Now first of all, we will prove that this splitting H is injective. So this is our claim. We claim that H from m double prime to m is injective. It is given that this H is a homomorphism. Now we have to prove it is basically an injective homomorphism. Now to prove H is injective, it suffices to prove this kernel is trivial, i.e. we have to prove kernel contains only one element, i.e. 0. So if we choose any element x in kernel of H, we have to prove x is 0. So let x belongs to kernel of H. Now if this is the case, so one can note here this kernel of H is actually a subset of m double prime. So if this is the kernel of H, then H of x will be 0. But this composite map G composition H, this is actually identity map on m double prime. Now if this x is in kernel of H, so this x is in m double prime. So if x is an element of m double prime, then G, when I operate G composite with H on x, I get x, because G composite with H is actually identity on m double prime. Now this x, this is same as G composite with H of x. Now this x being an element of m double prime, we get G composite with H of x is x. So this is same as G of H of x, but H of x is 0, so this is G of 0, but G being a homomorphism, we have 0 here. So we have chosen this x arbitrarily in kernel of H, and we have proved that this x is 0. That means this kernel of H is trivial. Therefore H is injective. Therefore H is injective. Now next we have to prove this M is direct sum of these two modules. Now to prove this, we have to prove M is actually f of m prime plus h of, I have to prove any element in M can be expressed as an element of f of m prime and an element of h of m double prime uniquely. Now there are a few ways to prove this claim that this M is direct sum of these two modules. Now for this I'll pick any element in M. So let M belongs to M be any element. Now what I'm going to prove this M is actually this M can be expressed as an element of f of m prime and an element of h of m double prime. Now if we look at this element here, so if I look at this element x minus hg of x, this is actually an element of M. Let us see how. First of all, this x, this belongs to M. Now hg of x, so hg of x is actually a map from, so G is a map from M to M double prime, this map G, and H is a map from M double prime to M. So this composite map hg, this is a map from M to M. So hg of x, x being an element of M, so hg of x, this will be an element of M. So this is an element of M here. This is also an element of M, so their difference is an element of M. So consider the element x minus, not x, I mean M. This is actually M here. So hg of M is, so M minus hg of M, M minus hg of M. This is an element of M because M is in M, and this hg of M is also an element of M, so is their difference. Now consider the element M minus hg of M. We have so if I operate, so now this element here being an element of M, so we can operate G on it because M minus hg of M is an element here, so this is an element in this set, so I can operate G on this set. So we have G of M minus hg of M. This is actually, now G being a homomorphism, we have this is G of M minus G of hg of M. This is same as G of M minus G of H of G of M. Now G of H is identity on M double prime. Now G of M will be an element of M double prime. So G of M is in M double prime. So now if this is an element of M double prime, so if I operate this map GH on this element, I get back GM because G of H is identity on M double prime. So this is GM minus GM. The reason being G of H is identity on M double prime and GM being an element of M double prime. So this is 0. Now if this is 0, that means this element over here, this is in kernel of G. Therefore M minus hg of M, this is in kernel of G. Now this kernel of G is same as image of F, and image of F, now F being injective homomorphism, so image of F is same as F of M prime. So this is F of M prime. Now let us look at this element. Also this X can be written as, sorry, this M can be written as this M is same as hg of M plus X minus, or let us write this as, so this is M minus hg of M plus hg of M. So we have proved here that this element, this is in f of m prime. So actually this is in kernel of G, which is equal to image of f, which is f of m prime. So this is actually an element of so this belongs to actually image of f plus now h of G of m. So this is simply in image of h. Now since f and h are both injective, this is same as this is same as f of m prime plus h of m double prime, because f and h are both injective and f is a map from m prime to m and h is a map from m double prime to m. So we have proved first thing. We are halfway done. Now to prove m is actually direct sum of these two submodules. Now to prove this thing, it remains to show that their intersection is actually trivial. So we have to prove f of m prime intersection h of m double prime is actually singleton set. This singleton 0. Now to prove this thing, let us pick any arbitrary element in their intersection. So let y belongs to f of m prime intersection h of m double prime. So if this is the case, now if y is in h of m double prime, that means there is some element z in m double prime such that y is h of z. So this implies let us write on next page. This implies this y is h of z for some z in m double prime, because this y is in h of m double prime. So therefore this y is h of z for some z in m double prime. Also this g of h, this is identity on m double prime. This means that if I operate g of h on z, I will get back z. Also this z is same as g of h of z, because this g of h is identity on m double prime. So this is same as g of y, because h of z is y, but y is in f of m prime, but f of m prime is same as image of f, which is same as kernel of G, because the sequence is exact. So this means if y is in f of m prime, that means y is in image of f, but image of f being equal to kernel of G, that means this y is in kernel of G. So this, therefore g of y is 0. The reason being, since y is in kernel of G, so that means this z is 0. Now if z is 0, then y is h of 0, that is 0. Therefore y is h of 0, which is 0. This means hence this m is actually direct sum of f of m prime, direct sum h of m double prime. But f being injective, f of m prime will be, this will be, so this is actually f of m prime is isomorphic to m prime, and h of m double prime is isomorphic to m double prime. The reason being f and h are both injective. So this is so their direct sum is therefore the direct sum of these two modules. So this is actually direct sum of m prime and m double prime. So this is therefore an observation. So whenever we have a separate exact sequence like this, so 0 goes to a goes to b goes to c, and c goes to 0. So if this happens to be a separate exact sequence, then this b is always, we can always express this b as the direct sum of a and c. Now we have this corollary here. So this states that, so let us consider an exact sequence. So let 0 goes to a, or say m prime, by, we have this morphism here, module homomorphism, and we have homomorphism G from m to m double prime, and then we have 0. So if this is a split exact sequence of R modules, then there exists an R module homomorphism say S from m to m, say from m to m prime. So we have this morphism here, S, such that this composite homomorphism S composite with F, so S composite with F will be actually a map from m prime to m prime. So this is actually the identity on m prime. So let us prove this. So since the given sequence is separate exact sequence, since 0 goes to m prime goes to m goes to m double prime, and 0, so this is f, this is g, is separate exact sequence therefore we have this m is actually, this is a split exact sequence. Let us mention splitting here. Or let us write this down as, so if this sequence is separate exact sequence, then this m is actually isomorphic to m prime and m double prime, direct sum of m prime and m double prime. So therefore we have m is isomorphic to m prime direct sum m double prime. Now let us actually, this is same as, actually this is same as f of m prime direct sum h of m double prime, where h from m double prime to m is splitting. So this is splitting. Now we can define a map. So now this changes to the equality. This is isomorphic to m prime and m double prime. Now we can define a map from m to this module here. So define pi from m to f of m prime. So obviously this is the projection map on the first component. Now every element of m can be expressed as an ordered pair. Say if m is in m, this m can be expressed as an odd pair of f of m and h of and some element here. So let us we can write this as an element of m prime and so this m can be uniquely expressed as sum of m prime plus m double prime, where m prime is in big M prime and this little m double prime is in this big M double prime. So we can identify this element here with this ordered pair. So now we are defining this map m, so it takes m to the first component, that is m prime. We do not need to write this down here, so it is just to make it clear how this map is given. So this is actually the projection map on the first module here. So this is actually a module homomorphism. So define this to be the projection. Now let us define this S. So let this map S, which we have to exhibit, so let us define this map S to be the map F inverse composed with this projection map pi. So obviously pi is a homomorphism, F inverse is a homomorphism from M to F of M prime. So this is actually a homomorphism from M prime to M prime. So clearly S is a homomorphism because it is the composition of homomorphisms. Now let us look at this map. Now consider the map S of F. So F is actually a map. So this is actually, so S of F is same as f inverse pi f, because this s is equal to f inverse pi. So this f is actually a map from m prime to m. So this is our map f. Then we have to operate s, but s is same as f inverse pi. So pi is a map from m to f of m prime, and this f inverse is map from f of m prime to m prime. So therefore this s of f is actually, now consider the map SF, which is a map from m prime to m prime. So indeed this is a homomorphism. Indeed S of f is a homomorphism. Now let us look at what happens when we operate this element to some element in m prime. Also SF of m prime, which is same as S of f of m prime. So S is same as f inverse of pi of f of m prime. Now since pi is the projection on the first component, so this is same as, so this is f inverse of f of m prime. So this is m prime. So this is true for all m prime in m prime. In other words, this map S of f, and this is actually the identity map on m prime.